So, good morning, class. It's my hope that you're well. I intend to. You're well. It has been a while since we last met. So, first of all, I really hope that you had a good time with the exams and that you're able to complete your exams, that the exams, now that you're in fourth year. And I also want to wish you well as you start your preparation for the fourth year exams. Part of what you'll be doing is what you'll be covering today in this particular lesson, in this particular unit. So I welcome you again to Com 417. For those who joined very late, this is computer graphics, and I hope that you'll be able to catch up. So far we did an introduction, we introduced ourselves to computer graphics, and then we looked at the mathematical. Of course, during the introduction we covered the terms which are used common in computer graphics, and it is good if you look at what we covered. And then of course we did a mathematical background. Computer graphics has a lot of mathematics. It is especially to do with algebraic, vector and matrix algebra. And then of course the transformation that we shall be discussing in lesson 5, and also the implementation of the curves. All this has to be with algebra, and that is why we need this lesson to come early on. That's why we did mathematical background, and together we did matrices, we also did vector, and we saw how you can add carry out arithmetic on them and multiply, but then add addition and multiplication is what we dealt with mainly. So we will have a look at that. You can go through this particular lesson to have a recap on that. In the third lesson we looked at Opengl, and remember we said that Opengl is just is a set of 3D functions or procedures for graphical manipulation. This is a standard, that therefore is not a programming language by itself. Actually, most of those procedures are programmed using C, but we have platforms through which you can implement this. Either you can use, if you're using Visual Studio, you can use Visual C++. Alternatively, if it is enabled for Opengl, you can also use WebGL, which is a version of Opengl that runs on the web. And therefore because WebGL is open, is based on the browser, and I think latest versions of Mozilla and Chrome can support this open WebGL thing. It is important that you try out. I have discussed this extensively before at the end of lesson 3. Before we discuss curves, I introduce you to WebGL, so that you can appreciate that what you are learning, the concepts you are learning, are actually programmable, and you can get to see or view them in WebGL. So remember, when you're discussing WebGL, we went through the steps of, first of all, defining the canvas, and then in HTML contextualizing that canvas. Sometimes you're doing a little bit of formatting for the HTML, and then of course making use of JavaScript in order to contextualize, create the main program that contextualizes the canvas. Once the canvas is contextualized for Opengl, then now we have what we call WebGL. You can be able to invoke Opengl functions from that canvas. We call it a contextualized canvas, and we discussed that before we discussed curves. So the last lesson we had just before you guys went for a break for the exam was about curves, and when we're discussing those curves, we of course also had a look at I think I'm going to just display that briefly when we discuss about curves in lesson 4. Here it is. We basically discuss curves, ellipses and polygons, and there's a video I made to that effect. You can click on this link so that you can access that video and be able to appreciate the content which are there. I explained a lot to do even with what we had discussed in WebGL towards the end. This example actually is also a little bit explained there, so that you can be able to do it and test it. I've also explained you can run the code with by opening the HTML file in Opengl enabled browser. So I've provided the codes. If you follow the links, and you're going to see that you can enjoy what is provided there. I think I better move this one here to be better off. Excuse me. Well, I think we can pick it up from there, but probably before we go to lesson 5, I would also like to highlight a little bit of what was there in lesson 4 when you're discussing about the curves and the ellipses and the polygons. We went through parametric curves, the ellipses, the properties of the ellipses, the polygons. I've restructured this course a little bit, of course, to discuss about the surface, normal, polygon, soup, meshes. This is just a restructuring of what you're seeing here, but otherwise the content remains the same, so that when you're doing your revision and you come across issues to do with the surface, normal, polygon, soup, and meshes, you can be able to know where these are found. And of course, it's good to understand what they are. I had mentioned them last time. When you have a polygon soup or a mesh, it's something that takes a lot of resources when you want to render these on the screen, and therefore for that reason we need to work on hidden surface removal. There is an algorithm to that effect, and you're going to view it here. And of course, we also dealt with scan conversion, how we do scan conversion of we scan convert a line, a polygon, and the sweep line algorithm, which is used for that purpose. I would like us now to change our focus with regard to lesson 4 to this part, to the rendering of curves in Opengl. I had covered a little bit of it, but I realized the file was wanting. There's some content that was left out. So if you're able to access, I've already updated what is there online. I think you can download it and have a look at it. I would like you to have a look at see that we have made some new additions, more elaborate, and also explained the primitives and the functions which are used when you're rendering curves in Opengl. GL map 1 is one of the functions, but all these you do, as you're going to discover, you do them between GL begin and GL end, and use the display functions within that. Of course, you're going to have loops designed in the same manner you do them in C or C++. You are going to define the vertices, evaluate the coordinates, and you're going to have other functions like excuse me, other attributes like T1 and T2, which specify the range of the variable. And that will be represented. The other parameters you may see, GL map explained with the vertex coordinates, their meaning, so that you don't get lost when you get to see them. An example of one-dimensional functions that is implemented, which represents a line, of course, is what you're seeing in Bezier curve.c. This is implemented in C programming language. You can see a constancy defined, and then of course you go ahead to define the control points, and then initialize some of the functions and some of the variables, and then from there you now use the display function to work out the display of the lines. Once you execute that, the result is what you can see here. So this one is when the steps, remember that defined at the top, the constant defined at the top there. This one, the steps, these are the steps you're talking about. Is a constant defined for the number of, actually it is implemented in the form of a loop within it. The number of the number of iterations that is going to take place when this line is being drawn. And of course that is what you're seeing implemented in this form. This is when the steps are 5, and this is when the steps are 30. So this section you do not have it, and there is an explanation of the functions, if you want, the procedures used, and also the attributes. I would like now the code you have just seen can also be rewritten in this form, what you're seeing here. In other words, in one file of some sort, in one viewing, you can have all the code, let's say in one file. So you see, when you are having the display procedure or function is one that calls the GL flash, which of course does display the control points, which you see as continuous dots, which becomes the lines which are rendered as shown above. Now when you want to do two-dimensional evaluation, the evaluators will be used as follows. You define the evaluators with GL map 2, not GL map 1 like the other one. Enable them by passing the appropriate value of GL enable. Invoke them either by calling evaluate coordinate 2 between a GL begin and end pair, or by specifying and applying a mesh with GL map grid 2 and GL evaluate mesh. You have heard of the mention of GL enable and GL end. This is what you're seeing. This is what you're seeing here. GL enable, GL end, GL begin. GL begin is here, as you can see, and GL end. You can see how the evaluate coordinates are being called within the loop, and of course GL begin is used to define whatever that is being done within the begin and end where the actual execution of the program takes place. So this is basically tells you is a line that will be drawn, GL line strip. Let's now see a two-dimensional implementation of the same and how it's done. Of course, this bit you can do a reading by yourselves. I can't take you through all this. You can read about even the the procedures which are being used and the meaning of the various attributes or variables that are being used. If you it's similar to what you have at the top there. You remember the control points. Here we have one more worded, so we have 443, and then is an array of 3 dimensions. Void display function, you have seen that. We introduce the line strip here. We are going to be drawing several lines which are going to form 2 dimensions, as you're going to see, and you're going to use evaluate coordinate 2 because now it's as you're going to see. And then of course you can see that this is limited to 30 iterations if you want. That's what you're calling the steps. The color, of course, to ensure that the lines are colored this time round, they're not just in black and white. And even though in black and white, in gray, that's too a color to be defined. And of course the initialization you can see here: enable, map vertex 3, GL depth test. So these are what is and the shade model for flat shading. The output for the above code is this. You see the 2 now. This is in 2 dimension. That one is just a line. So and I would like you to try now using WebGL and see how you can render such a 2-dimensional diagram. It's like the way you render a triangle anyway. And see whether you can render this in WebGL now that you know about the primitives that are in use. I also want to mention here that as we progress now, I will not, if you can do it in Opengl that is available in your Visual C++ or Visual C, I mean in C, any C programming coding platform that is also enabled for Opengl, then it's okay. You can copy and paste these codes and work with them. I don't want to emphasize on the nitty-gritties of how we go about doing it because lesson 5 has a lot of mathematics in it, and we need to focus on the content also for the remaining time. I want to believe that once you learn how to do it in WebGL, you can map it to any other platform. Yeah, I was doing that to build your confidence that these things are viewable on the screen. So you can do it by yourself. Either you choose to do WebGL or you can try using whichever tool you have, especially for C or C++ that is enabled for WebGL. Thank you. Now that is for lesson 4. Which I would like you to revisit. I've already updated the file which was there to cover the extra bit. The only extra bit is actually what you have in 4.5 and 4.6, and of course the change of the discussion session. Now before we get to lesson 5, I would like to draw your attention to the new instructions that I've given. We have, as I had promised before the exam break, and due to the challenges we have, sometimes I have challenges with the network. I think my laptop has grown too old. It just sometimes disconnects. Even when there is network, it just disconnects from the Wi-Fi. So for that reason, it disrupts my online classes, which you are well aware of. So that's why I've recorded this class to share with you. I will proceed to record the lessons and share the audio. I will also have a quiz at the end of every lesson to ensure participation. Take note that when you listen, you need to listen to the audio, read the notes and other materials provided. Other materials sometimes will be, of course, YouTube videos that are found relevant that are online, like this one on transformation, which I'll be sharing with you, which is relevant for this lesson 5, so that you can better understand the content. And of course, at the end of the lesson, there will be a quiz, and every quiz will be done within the day set for the lesson, as shown below. So for lesson 5, of course, we are doing lesson 5 today, but I'll expect that by tomorrow, Thursday, you attempt the quiz for lesson 5 and onwards. For Friday, the quiz for lesson 6. For Monday, the quiz for lesson 7. For lesson 8, for lesson 9, for lesson 10 by Thursday. In other words, after Thursday, you shall be through with the entire coverage of the entire lesson. This is a way to ensure that we read through the material and that we at least have an idea of the concepts, so that if we are even to ask a question, we ask a specific question in the forums. I will create forums just in case you want to draw a question online. Having said that, I hope that you're going to cooperate. This is personally, I intend actually to prepare these lessons well in advance, so that you can actually read these lessons over the weekend. probably even complete them at the end of the quiz if you're that fast. Alternatively, you have the time up to Thursday to have completed. Target actually to complete by Wednesday so that you give yourself time on Thursday to catch up. Once you're done with that, then you shall have been through the course, and after that we can discuss with your class rep and find out whether it will be relevant for us to have one cut to cover the entire content even as we prepare for the exam. Having said that, I would like us now to look at lesson 5. I've activated the material. The other thing I've done is that I've activated all the materials. If we go to lesson 5 here, the lesson 5 is on transformation. I've activated the material, meaning that you can view the content, and that goes for even the other contents in lesson 6, lesson 7, lesson 8, lesson 9, lesson 10. All of it is visible to you now, unlike the way I was making it visible per week. If you want to read ahead, feel free to read ahead. Now in lesson 5, which is about transformations, I would like us to quickly go through it. Basically, we are going to be looking at what are transformations. We are going to look at the various types of transformation we have. Specifically, we shall deep dive on affine transformations, homogeneous coordinates, hierarchical transformation, and transformations in Opengl. How do you implement those transformations in Opengl? And then a discussion session, which is basically a question which you can go about reading for yourselves and attempting. So transformation basically is the process of modifying and repositioning the existing graphics. And transformation is a term that basically means changing some graphics into something else by applying some rules. We can have various types of transformation, such as translation, scaling up or down, rotation, sharing, etc. I mean, when we talk of translation, it means we are applying, it reduces down, mathematically it reduces down to a function that transfers one matrix from one value to another value. In other words, from one we can call it matrix values into another matrix value. Same case for vectors, either by addition, or that is or multiplication, which is scaling up or down, or by rotating, that means adding a new angle, or by shearing, changing, holding some of the coordinates into a specific base location and changing the other coordinates in order to implement shearing. When a transformation takes place on a 2D plane, it is called a 2D transformation, and we also have 3D. Transformation play an important role in computer graphics. For instance, they used to change coordinate frames. You have world, window, viewpoint, device, etc. They used to compose objects of simple parts with local scale, position, orientation of one part defined with regard to the other parts. For example, for articulated objects, they are useful for deformation to create new shapes, useful for animation. And we have 3 basic classes of transformation. We have rigid body, which preserves the distance at angles. Example, we have translation and rotation. Then we have conformal transformation, which basically preserves the angles. Example, we have translation, rotation, and uniform scaling. These ones preserve the angles. Even uniform scaling does not change the angles. We have affine transformation, which preserves the parallelism. In other words, lines remains lines, and if they are parallel, independent of their transformation, they remain parallel to each other. We have translation, rotation, scaling, shear, and reflection. These are critical. They're important. All these are important for computer graphics. And in fact, before probably we get into affine transformation, I would like us to have a look at a graphic that illustrates what we have just said. A translation is like what you're seeing. Take note, what appears in gray or black is basically the original shape. What appears in blue is a transformation. So a transformation of a translation type takes this form. We translate and therefore probably move the various. When it becomes a vector or a matrix, then it means we are moving the coordinates to another location in entirety, so that the diagram seems to have moved. When it's scaling, it's basically holding one of the locations constant and increasing the other coordinates. That way we scale it up. In other words, we increase its size or reduce its size. When it's shear, we make it change in shape by holding some of the coordinates and of course moving other coordinates at an angle. And as you can see here, we have shear illustrated with the rectangle now looking like it is bent, like it becomes a trapezium. Then we have rotation. It means now the shape seems to be changed with the with the width and the height acquiring different directions of some sort. So and therefore the entire diagram seems to be rotating. The corners, the vertices are in different positions, all of them. The coordinates have changed the locations. That's how to view it from a matrix point of view. So now, having talked about that, I'd like us to go back and look at these examples of transformation, which we are calling affine transformations. Leads us now to a better understanding of this particular subtopic on affine transformation, which is a linear mapping method that preserves points, straight lines, and planes. Sets of parallel lines remain parallel after an affine transformation. And the affine transformation technique is typically used to correct for geometric distortions or deformations that occur with non-ideal camera angles. For example, we have satellite imagery that uses affine transformation to correct for wide angle lens distortion, panorama stitching, and image registration. When satellites actually work at a distance in space, although they really also within the external boundaries of the Earth's atmosphere. Sometimes for purposes of things like remote sensing in geographical information systems. So the kind of images we get from these satellites have to be transformed automatically. We get images which are already transformed, so that to correct for the error that comes with the wide angle lens distortion. So these images are transformed and fused to a flat coordinate system, which is desirable to eliminate distortion. It enables easier interaction and calculation that don't require accounting for image distortion. We don't have to do the computation, probably do a little bit of punch sharpening, which is done using GIS tools. So that's for an example of satellite imagery and how affine transformation are used to make corrections. And these are the types of transformations we just discussed. Now, homogeneous coordinates. We go to the mathematical. With this, we illustrate mathematically how these transformations happen. To convert a 2 by 2 matrix to a 3 by 3 matrix, we have to add an extra dummy coordinate. Let's say W. We understand that 2 by 2 matrix to a 3 by 3 matrix. Then we add a dummy coordinate. In this way, we can represent the point by 3 numbers instead of 2 numbers. This is called homogeneous coordinate system. Excuse me. In this system, we can represent all transformation equations in matrix multiplication. With homogeneous coordinates, affine transformation become matrices, and composition of transformation is as simple as matrix multiplication. So if we have homogeneous coordinates, a point, let's say P, is augmented with another point, let's say 1, to form a matrix P, which consists of the point and the other point 1. Now all points, let's say alpha, point P, alpha, represent the same point P for real alpha, where alpha is equal to 0. And of course that we can well understand that if this is 0, of course, we have the original point P, because this will be 0 and this will be 0. We are left with the point. Given P is the matrix is in homogeneous coordinates, to get the point, we divide P by its last component. This component now, this one. We divide P with this alpha. Once we divide P with alpha, we have, for instance, this one becomes 1, this one becomes 1, then we get the original value of this point, and then we discard this, the last component. We discard this last component, and we're left with the original point. How does that happen? The homogeneous points, let's say 2, 4, 2, and 1, 2, 1, are both represent the Cartesian point 1, 2. We understand the Cartesian point. This is x, y, forming one point. 1, 2, meaning this can be reduced. If you divide this by 2, you get 1, 1, this becomes 2. Therefore, the point to be, then you discard this one. The point being represented here is 1 and 2. It's like discard with this one, and you're left with the point. Is the orientation of, it is the orientation of P, the point, I mean the matrix that matters, not its length. Many transformations become linear in homogeneous coordinates, including affine transformation. And of course, this is a generalization of what we have just discussed about the adding of new, the particular transformation we are discussing here and how it's taken. I'll be showing you a video on how this transformation takes place, and I think you're going to appreciate it. When it appears like this, it can look scary because of the letters, and but you can see these are 2D, and of course, when we introduce excuse me, when you introduce tx and ty transformation coordinates, then we have a factor, and then we of course do the matrix, then we get the new vector, and we have the transformation. To produce the matrix Q, I mean the matrix Q rather than the point Q, we add a row to the matrix. So we pick the matrix here and add a row. This is 0, 1. So we have 0, 0, 1, and of course this row now is added, creates what you're calling the matrix instead of the point. With homogeneous coordinates, the following properties of affine transformation become apparent. Affine transformations are associative, meaning if we have we have a matrix like F1, F2, and F3. If a multiplication of the product of F3 and F2 to F4, the product of these to F1 is the same as the product of F3 to the product of F1 and F2. However, they are not commutative. In other words, if you multiply F1 by F2 by F1, it's not the same as multiplying F1 and F2, and you know this from matrices. The important operations that can be performed correctly in terms of homogeneous coordinates can be done as follows. So affine transformation is an important case. In the previous section, is applying. We are looking at an important case we have just illustrated in the previous section of an affine transformation to a point in homogeneous coordinates. So if we have a point Q, and then we apply a homogeneous transformation to it, what we get, of course, is the transformation of that point, and the transformation of that point becomes now x, y, the transformed, and of course, you know, the new added coordinate alpha, and then it is easy to see that this operation is correct, since if we now want to go back, we just need to divide with alpha and get the results, which now we reverse with 1 again. Vectors we can represent a vector, let's say v, as a point xy in homogeneous coordinate by setting the last element of the vector to be 0. So if we set this last element 0, you know, this last element is show direction. That means we have introduced a vector. The only thing we need to know when we do that is that when adding a vector to a point, the point must have the that component as 1. Otherwise, it will lose meaning. So that's what you're having a illustration here. So we want to get to add a vector to a point, and so we are adding this transformation to this matrix and this vector. So the result is clearly incorrect if that component of the vector is not 0, so it has to be 0. In other words, it's like you're not giving it direction. Note, homogeneous coordinates are a representation of points in projective geometry. Now, hierarchical transformation, on the other hand, are concerned with modeling objects as hierarchically connected parts. How do we model complex objects and scenes? We describe everything as a single complex model. We describe everything. If we describe everything rather as a single complex model, it should not be a good idea. This is what you try to avoid even in lesson 4 when we are talking about the surface, the polygon soup and meshes, and how we need to do hidden surface removal to remove the complexity that goes with it. In the same way, when you are modeling complex objects, we should avoid describing everything as a single complex model. That would be too heavy. So we use hierarchical modeling instead. So we're starting with the basic set of 3D primitives, cubes, spheres, and prisms, and each is defined in a nice way in its own space. We put primitives together, we use transformations, and then each transformation embeds one space in another, and then we use a whole hierarchy of spaces to build up the complex models. Not just one model space, but one for each model and part of a model. How do we implement this transformation in Opengl? They are implemented in 2D, and we have 3 basic kinds of transformation in computer graphics. We have translation, rotating, and scaling. When you're actually implementing them all together, you start with the translation, then go to rotation, and then scaling. You follow that specific order for the benefit of not having challenges when rendering that on the screen. So we have, when you want to do a translation in computer graphics, you use a function, an OpenGL function called GL translate f. In other words, translate function. It takes three parameters, tx, ty, and tz. Now, of course, tx and ty are translation coordinates. Translation itself refers to moving an object to a different position on the screen, like this line now. When you move the entire object, looks like it has excuse me. The object may not change in size actually, but may be moved to a different location. I think we had seen that also here. It has not changed in size, but has been moved. And of course, tx and ty are the translation coordinates. If in 2D, of course, that means tz would take the value of 0. Rotation refers to rotating a point, and here, of course, we have the scenario where we use angles. X cos A minus y sin A. A little bit of trigonometry will come into action. Even in the Cartesian coordinates, is actually the angle of concern here is the angle of rotation is angle A, what you're seeing here. For the x coordinate, then we have x cos A minus y sin A. For y coordinate, we have x sin A and plus y cosine A, the cosine of that angle. So you're taking the cosine of the angle and multiplying it by x and subtracting that with the sine of the angle multiplied by y. Then for the y coordinate, you are starting with the sine of angle A multiplied by x and cosine of angle, add that to the cosine of angle A multiplied by y, and you get the value of the y coordinate. So that formula is used to rotate the point around the origin, and when that happens, then you of course, if you want to rotate around a different point, the formula changes slightly into what you're seeing here. This is just an extrapolation of this, where this x now, this x you're seeing here, becomes cx plus x minus cx. In other words, to reference this point with regard to show the change of that point with regard to the of point x, by how much it increases, for instance, the rotation, the angle, so that eventually we are able to reference this point with the point x with regard to the change which is taking place. So if we have doing it around a different point, then the formula becomes, aside from the origin, then the formula becomes this. Those are rotations. Then you have scaling. Scaling is just multiplying the vector, or if you like, the matrices by a factor. So the point x will be multiplied by a factor sx, the point y will be multiplied by the scaling factor sy. So sx and sy are scaling factors, and the OpenGL function that is used is the scale function, as you can see, which takes the float x, y, and z. The OpenGL function for rotate is easy to remember. GL rotate function, angle A is the rotation angle, x, y, z. So the only thing you need to feed here is the angle. These are the coordinates. Now, if you have combined the translation, remember I mentioned these transformations, then you apply them in the order of translate, rotate, and scale. I would like you to now try at your free time to develop C code to implement basic transformation in OpenGL. And you can also try to use WebGL if you already become comfortable with it. Well, this is it. But before we sign off from this lesson, I would also like us to probably have a look at how that is done. I have some videos that I'm going to share with regard to these transformations, and I hope we don't have so many adverts. Just so you have time, I'll attach them so that you
Hey everyone, if I had to choose just one topic that makes
Just
all of
listen
the
and
others
read.
in linear algebra start to click, and which too often goes unlearned the first time a student takes linear algebra, it would be this one. The idea of a linear transformation and its relation to matrices. For this video, I'm just going to focus on what these transformations look like in the case of 2 dimensions, and how they relate to the idea of matrix vector multiplication. In particular, I want to show you a way to think about matrix vector multiplication that doesn't rely on memorization. To start, let's just parse this term, linear transformation. Transformation is essentially a fancy word for function. It's something that takes in inputs and spits out an output for each one. Specifically, in the context of linear algebra, we like to think about transformations that take in some vector and spit out another vector. So why use the word transformation instead of function if they mean the same thing? Well, it's to be suggestive of a certain way to visualize this input-output relation. You see, a great way to understand functions of vectors is to use movement. If a transformation takes some input vector to some output vector, we imagine that input vector moving over to the output vector. Then to understand the transformation as a whole, we might imagine watching every possible input vector move over to its corresponding output vector. It gets really crowded to think about all of the vectors all at once, each one as an arrow. So, as I mentioned last video, a nice trick is to conceptualize each vector not as an arrow, but as a single point, the point where its tip sits. That way, to think about a transformation taking every possible input vector to some output vector, we watch every point in space moving to some other point. In the case of transformations in 2 dimensions, to get a better feel for the whole shape of the transformation, I like to do this with all of the points on an infinite grid. I also sometimes like to keep a copy of the grid in the background, just to help keep track of where everything ends up relative to where it starts.
Now, gentlemen, I think you have seen the graphical representation of the transformation we are talking about. There are other videos I'll be sharing with you. I'm going to try and select the best among them, so that I'm thinking of sharing these two, so that you can appreciate what is there in transformations, mainly translation, rotation, and scaling. With that, you can be able to appreciate and better understand the ideas that we have shared in lesson 5. So I think we're going to stop there for lesson 5, and I hope that you're also going to download this lesson and go through it. Thank you very much. I'll also have the quiz ready before the end of the day, so have a look at lesson 5, this section. We're going to have a quiz, and read the content, and also watch the video, watch my audio, listen to my audio, watch the video and listen to it also, then attempt the quiz. I believe once you do that, you'll be in a better position. You feel free to ask me questions, either by calling my phone number. If you have it, you can get it from the class rep, or even by just simply typing it in the forum, which I'm going to be adding as an activity here. Thank you, and have a great day.